Hello, welcome back to another video. I am Professor J-Dog, and today we're going to be going over question 1.13, the magnetic circuit of this figure. The parameters are given, and we're asked to calculate A through E. I'm only going to do A through D. E, I'm not sure of my reasoning, so I'm not going to be completing it. If anybody has a solution for E and has an easy way to explain it, that'd be greatly appreciated. Anyways, without further ado, here's the problem at state. Our parameters Ri are given, Ro, H, G. For this problem, the way to tackle it is to really understand just the different lengths that are given. So Ro is going to be the length from the center point to the outside of the magnet. Ri is going to be the inter, so that we have an outer radius and an inner radius, and we're going to need to first calculate LC, which LC is the mean core length, which basically just means there's a current. So this winding from this inductor provides an upward current around here, and the core length would be directly in the middle of these two sectors. So if we take RO and RI, it's going to be, the difference between the two is going to be 0.9. So the centimeters in between is going to be 0.9. So let me write this. So 4.1 centimeters minus 3.2 centimeters is going to be 0.9 centimeters. So that's going to be the distance, this distance here, 0.9 centimeters. In the middle of that is where that current's going to lie. That's where we're going to need to calculate the length of the core. So the length of the core is going to be directly like half of this, which is going to be 0.45 centimeters. Now from the center is going to be the circumference of that middle portion, right? So if we take Ri, which is 3.2 centimeters, and add 4.5, we're going to add 0.45, 3.2 centimeters. Right, this is going to be equal to 3.65 centimeters, which is going to be the radius from the center point to this line, this dotted line that we're trying to calculate circumference. And now a circumference of a circle is going to be 2 pi r, which is the LC, which is the circumference, which is the length of the core. And our r in this case, you would think, right, it'd be 3.65, but it'd be 3.65 centimeters minus 0.15. Why? Because there's a gap. So we're going to go all the way around the circle, and we're going to subtract that length, that little tiny gap that we're not considering as the length. So, perfect. So this would equal 22 centimeters. Perfect. So that'd be the length that we walk around this entire thing. So now we're asked to calculate AC. Perfect. AC is the area, right, of the core. And so if we draw this out, we have basically like a box, and we know this is 1.8 centimeters as the height because it's given here of this stack. I mean, you can write it here or here, but an area is just like length times height. So 0.9 centimeters. So if we do the length, this cross-sectional length multiplied by the height is going to give us the area. So the area of the core is just going to multiply these two, which AC is 1.62 centimeters squared because it's an area. So now we have these parameters here. LC and AC are calculated. Now on to B. So B, there's two formulas for the reluctance. So the reluctance of the core, that one, and then we have the reluctance of the gap. And RC is equal to LC over mu AC, and then RG is equal to the gap divided by mu naught times Ag. So these two formulas, you can derive them, or you can just write them on a formula sheet. LC, we calculated over here, but RC, since it's given in the equation that mu is infinity, if mu is infinity, then this whole thing goes to 0. Goodness, I'm writing at like a weird angle, so sorry. So RC is, this whole thing goes to, the bottom, the denominator goes to infinity, so this goes to 0 as mu approaches infinity, right? So RC is equal to 0, RC is equal to 0, and now RG is going to equal the gap. So we already know G is given up here as 0.15 centimeters, divided by mu naught, which is a coefficient. So mu naught is equal to 4 pi times 10 to the negative 7 henries. And then this is a this is known. This is always the case. Mu naught is always 4 pi times 10 to the negative 7. This is standard. So mu naught Ag, perfect. Ag, we already calculated it here because AC, right, area of the core is going to be the same thing as the area of the gap because it's just an area. This small sector has the same area. AC is equal to Ag. And we already given that here. So when we plug that in, right, we can calculate Rg is 7.368, 10 to the 6th. Perfect. And then now for n amount of turns. So we calculated these. These do not need, you don't need to know how many turns. We're just calculating from our basis of our magnet these parameters. But this is structuring it to set up for finding inductance, because inductance relates current, which also you can find current, but you need to know how many turns because it's an inductor. So the amount of turns will tell you the amount of current with said formulas. Okay. So for this specific magnet here, we can draw a circuit equivalence, right? Okay, and so we have a source. Perfect. And we have RC, RG. Okay, so here's a source. For this inductor, we can write it as a source because this is a source here supplying, and this is F equals Ni, the amount of turns, times I is equal to this source here. And here is phi, which phi acts as our current, and RC, we can relate these as resistors. So RC and RG, they're two different areas, so they have two different resistances. And then we can calculate the current I for this loop. So R total is equal to RC plus RG. Added those two resistors because they're in series, so you can add them together to find R total. And then for the inductance, we have L is equal to N squared over R total, which is just the formula for inductance. And we know the amount of turns. So 72 squared over RC plus RG. So RC plus RG, we know RC is 0 and RG is 7.36. So this would be 0 plus RG, right? Which would equal 7.034 times 10 to the negative 4th henries. So this is the inductance considering RC is 0. So we're just doing N squared over RG because our total, we neglect RC since this goes to infinity in the denominator. And so pretty much from there, you can also calculate current. So current I, let's do I, is equal to N times B, EG, times AG. Perfect. Divided by L. And so BGAG, right here, this is equal to V, which is the current of our circuit. So if we do N times I, right, which is our F, so you can do I is equal to F over L, and our F is equal to NI, right, over L, and then R, which is also equal to N times BGAG over L. If that kind of gives you more perspective, equals V. Yep, I'm sorry. And then lambda is equal to L times I. L times I. And so we know what I is here, and we just plug in. So I equals 72 turns times BG, which we're given 1.25 T. And that is given in the equation. I'm trying to show, maybe I have it right here. Yeah, right here. This is given, I'll show you guys here. It says operate an air gap flux density, BG equals 1.25 T. So, that's my solution. So, 72 times 1.25 T, can just these units out, times 1.62 times 10 to the negative 4. All over L, which is 7.034 times 10 to the negative 4, which we calculated from here. Pulling these all together, our I is equal to 20.7 amps, and then our lambda value is equal to 1.46 times 10 to the negative 6 WB. So these are just more units, Webbs, specific units, amps, henries, and LC/AC. Here's the complete solution for 1.13. If there is any questions or you need further explanation on this entire process, feel free to let me know in the comments. You can email me if you have any questions. Thank you so much.